Welcome to the second lecture on C-star algebras titled the Gelfand-Naimark Theorem. Let's review our previous lecture. A C-star algebra is a Banach algebra together with an anti-multiplicative conjugate linear involution star, also called the adjoint, such that for any element A of the C-star algebra, the norm of the adjoint of A times A equals to the square of the norm of A. A star morphism between two C-star algebras is an algebra morphism which intertwines the adjoint operations. A unital star morphism between unital C-star algebras is always continuous and of norm 1. Moreover, a star isomorphism between unital C-star algebras is always an isometry. If an element A of a C-star algebra is so-called self-adjoint, which means it equals its own adjoint, then the norm of that element A is in fact the spectral radius of A. As an example, if X is a compact Hausdorff space, then the space C of X of complex-valued continuous functions over X is an Abelian unital C-star algebra. In this lecture, we are in fact going to study the structure of Abelian unital C-star algebras. Let's start with an interesting observation. Let's be given some compact Hausdorff space. If we pick a point x in that space, we can define a continuous linear functional on C of x, which to any function f in C of x associates its value at x, f of x. And this continuous linear functional is actually multiplicative. Conversely, if we take any continuous linear functional over C of x, which is multiplicative, then applying the Ritz-Radon theorem and some basic measure theoretic techniques, it turns out that there exists indeed a point in our x in our compact Hausdorff space such that omega is given by delta x. So we have essentially shown that the concept of a point in a space is reflected exactly at the level of the C-star algebra C of x in terms of what we are now going to dub characters, that is, certain kind of multiplicative linear functionals. Specifically, a character of a unital C-star algebra is a non-zero algebra morphism from the algebra to the complex numbers. Let's start with a simple observation. Let omega be a character. Let's compute omega at the unit of our C-star algebra. So omega of 1 is equal to omega of 1 squared, which is, because omega is multiplicative, the square of omega of 1. So solving, we see that omega of the unit of your C-star algebra must be either the number 0 or the number 1. However, if omega of the unit is 0, then for any element A in your C-star algebra, you can calculate omega at A, and that's the same thing as calculating omega at A times 1, because of the definition of the unit of a C-star algebra, which in turn is omega of A times omega of 1, because omega as a character is multiplicative, and omega of 1 being 0, we get that for any A in your C-star algebra, omega of A is itself 0. That contradicts the idea that omega is a character in particular. It's a non-zero algebra morphism. So a character must always assign the value 1 to the unit. Of course, if you have an algebra morphism from the C-star algebra to the complex numbers which assign 1 to the unit of the C-star algebra, well, then it's not a zero morphism, so this is a characterization of characters. Now, what I'm going to show is that characters are in fact examples of unital star morphisms from the C-star algebra A to the C-star algebra of the complex numbers. To do so, we're going to proceed through 3 steps. So if omega is a character of a unital C-star algebra, then the first thing I'm going to prove is that for any element A of the C-star algebra, the character omega applied to A gives me a value in the spectrum of A. Then I'm going to deduce from this that actually a character is automatically continuous, and in fact it has norm 1. And last, I will apply those results to show that indeed for any element A of my C-star algebra, omega of the adjoint of A equals to the conjugate of omega of A, which is to say, since we already have that omega is an algebra morphism, that it also intertwines now the adjoint, and thus it is a star morphism. It is unital as we observed in the previous slide. So let's start with our first observation. Let's pick an element A in our C-star algebra, and let's assume that for the character omega, omega at A is not an element of the spectrum of A. So that means, by definition of the spectrum, that A minus omega of A times the unit of A is an invertible element in our C-algebra. So let's pick an inverse. Well, the inverse is only one, call it B. So we have thus a B, so that B times A minus omega of A at the unit times the unit is equal to the unit. But then we can apply the character omega to this equality on both sides, remembering that a character assigns 1 to the unit of our C-algebra, so we get that 1 is equal to omega of B times A minus omega A times the unit of the C-algebra. And then we do a simple algebra. We use the multiplicativity of omega and expand, and we see that everything cancels, and we're left with the identity 1 equals 0. This identity being absurd, we conclude that we must have, indeed, that omega of A is in the spectrum of A. Now, the second observation, which follows immediately now, is that if you pick again an A in your C-algebra, since we know that omega of A is in the spectrum of A, then we must have that the modulus of omega of A is less or equal than the spectral radius of A. That's the definition of the spectral radius. But the spectral radius, in turn, is less or equal than the norm of A. Therefore, we have indeed shown that certainly characters are, first of all, continuous linear functionals, and second of all, that their norm is at most 1. But on the other hand, we also show that characters are unital. They map the unit of the C-algebra to 1. And of course, the norm of the unit of a C-algebra is always 1. So this shows that indeed the norm of our character is 1. So now I'm going to prove the much more involved third point of the theorem. So the problem we're having right now is that a character was assumed to be an algebra morphism, and there was no information a priori about its behavior with respect to the adjoint. But because it is an algebra morphism, and a unital one at that, it actually behaves well with inverses. It preserves inverses. So what we're going to do is we're going to start with a simple observation. Let's pick an element U of our C-star algebra whose adjoint equal to the inverse of that element. So in particular, U is invertible. An element which is invertible and whose inverse is its adjoint is called a unitary. So U is a unitary element of our C-star algebra. Then, since U times U star equals the unit of the C-star algebra, we know that 1 equals omega of U times U star, but using the fact omega is multiplicative, 1 is in fact equal to omega of U times omega of U star. So, since omega of U and omega of U star are complex numbers here, we can conclude that omega of U star is the inverse of omega of U in the field of complex numbers. But on the other hand, we also have the C-star identity that tells us that since U star times U is the same thing as U inverse times U is the unit of A, and that has norm 1, we conclude that 1 is equal to the C-star norm of U star U, which is equal to the square of the norm of U. So, in short, the norm of a unitary is always 1. But characters are also of norm 1. So when you apply the character omega to the unitary U, you get a number whose modulus is less or equal than 1. Now, on the other hand, it's immediate to check that the adjoint of a unitary is a unitary. And therefore, in particular, omega applied to U star in modulus is also less or equal than 1, for the same reason as before. But on the other hand, that's equal to 1 over the modulus of omega of U, because omega of U and omega of U star are inverse to each other as complex numbers. So you conclude from these two inequalities that in fact omega of U in modulus is 1. So in other words, omega of U is an element of the unit circle of the complex numbers. And its inverse, which we know to be omega of U star, is actually the conjugate of omega of U, because that is how you take the inverse of a complex numbers on the unit circle. And so we've shown this red highlighted property in our theorem, but only in the special case when we work with a unitary operator. So to generalize our result from unitaries to arbitrary element of our C-star algebras, we're going to do an intermediate step, the key step really, which involves self-adjoint elements. So the reason why we are going to do this is because if you give me a self-adjoint element, I can make a unitary element out of it. And it goes like this. So let A be an element of your C star algebra so that A equals A star. And let's pick some real number t. My goal is to show that this element called u sub t on the third line here is actually well defined. And if you look at what u sub t is, it's a sum of a series which you really would like to call exponential ita. But we're in a C star algebra, we need to justify this series converge. So to do so, what we observe is that if we take the norm of the general term of that series, using the fact that we have actually an algebra norm, you see that we have a natural upper bound, and that natural upper bound itself is a general term of a very natural series. We immediately recognize a series whose sum is exponential times t times the norm of A, which is finite. So because the C star algebra is in particular a Banach algebra or even a Banach space, we can conclude that absolute convergence does imply indeed regular convergence in the actual algebra, and so u of t is actually well defined. And then it's a little exercise to check that if you take any t real number, u sub t times u sub minus t is indeed the unit of your C star algebra. That follows from the binomial theorem. Now you have to be careful in general when applying the binomial theorem in a non-commutative ring, and at the moment I haven't assumed my C star algebra is Abelian, though for the purpose of this lecture I might as well have, so you can always work with this assumption, you won't lose anything. But here I don't need it simply because the series involving the definition of u of t and u of minus t only involves commuting elements, namely things of the form ita or minus ita and their various powers. So the binomial theorem applies and we can check this simple identity. And this identity tells me, because you can always replace t by minus t in it, you see immediately that in fact that tells you that all the UTs are invertible in your C star algebra. Now, on the other hand, I can also calculate the adjoint of u of t. I'm going to do it to simplify my notations now in the special case of u of 1, so t equals 1. And the reason why I can do this calculation easily is because the adjoint is conjugate linear to begin with, but it's also continuous. We proved that in our previous lecture. It's an isometry, so it's continuous, so that the adjoint of u of 1 is actually u of minus 1, which we just saw is the inverse of u of 1. So our u of 1, and in fact this would be valid for any u of t, is a unitary. And with a little observation we made on the previous step of our proof, it tells me that for my character omega, the modulus of omega of u1 must be indeed equal to 1. We know that. But we can continue. What is omega of u1? Well, omega of u1 can be computed because we have seen in the previous 2 bullet points in our theorem, which we have now proven, that omega is continuous. So omega of u1 is equal to this series right here. I took the sum out at the level of the partial sum, then takes the limit out thanks to continuity. And you get that, well, we recognize this is exponential of I times omega of A. Now, omega of A, I don't know what it is. It's a complex number, that's all I know. But I can write it, of course, as omega of A equals the real part of omega of A plus I times the imaginary part of omega of A. And then you plug that into your exponential, and we get that omega of u1 is the product of this exponential of minus the imaginary part of omega of A times a unimodular complex number. So, in particular, we know the modulus of omega of u1, but that modulus must be 1. And we get this simple identity that the exponential of minus the imaginary part of omega of A must be 1, which in turn imposes that the imaginary part of omega of A is actually null. And therefore, omega of A is in fact a real number. Well, this is what we wanted to prove, because if A is self-adjoint, you know that this point that is still highlighted in red here tells me that omega of A is equal to omega of A star, because A equals A star. But therefore is equal to the conjugate of omega A. So for a self-adjoint element, omega of A is a number equal to its conjugate, in other words, a real number. And we have just shown that indeed this is true. So now we can conclude, actually. Let's take X an arbitrary element in our C star algebra. I'm going to write X as an obvious linear combination of two self-adjoint elements, so that I can apply my previous work. So the first thing is, I define those two self-adjoint elements in a way that's reminiscent, of course, of what we do with complex numbers. That is, I define the real part of x as x plus x star over 2, and I'll let you check that if you apply the star operation to that, you get indeed that it's still equal to the real part of x. Similarly, I define the imaginary part of x as x minus x star over 2i. And again, if you apply star to this, you get that the imaginary part equals to its adjoint. So we have two self-adjoint elements here. And it's immediately clear that x is indeed the real part of x plus I times the imaginary part of x, and this is just algebra. Just we do the calculation and it just works. But on the other hand, because we know that the real part and imaginary part are self-adjoint here, we can calculate x star as the real part of x minus I times the imaginary part of x. So you see it behaves a bit like a complex number. It's just a direct calculation. So we can apply omega to x star. Omega is linear, so we get that this is omega of the real part of x minus I times omega of the imaginary part of x. We could also have applied omega to x, and we would have gotten that omega of x is the real part, so omega of the real part of x plus I times omega of the imaginary part of x. So you can see that because omega of the real part of x and omega of the imaginary part of x are real numbers, we prove that because the real part and the imaginary part are self-adjoint, we can see that indeed we have shown that omega of the adjoint of x is the conjugate of omega of x. It is important here to use at this point that omega of real part of x and omega of imaginary part of x are real numbers, so that indeed we have the desired relation. And that's it. We have shown that our omega character here does intertwine the adjoint operations on A with the adjoint operation on the complex numbers, which is just a conjugation. So in particular, characters are in fact unital star morphisms from our C-algebra to the complex numbers. And it is immediately trivial that if I give you a unital star morphism from a C-algebra to the complex numbers, then it is a character. There is one more observation I would like to know before we move on. You could notice that we learned already that unital star morphisms are indeed of norm 1. They're continuous and of norm 1. So it seems that this third point in my theorem implies my second point in that theorem, which is technically correct. But the proof went the other way, and it's important to notice that. We needed the continuity of omega in our proof so that we could calculate omega of the exponential of I times the self-adjoint element in our proof. And to do that, I needed the ability to use the fact that omega was not just linear, but actually continuous. So even though when we get to point 3, we have a sort of aha moment that, of course, point 2 had to be true, but it is actually a corollary of it, rather than the other way around. So if you recall the discussion we had at the beginning of this lecture about points, then it is natural to form the set of all the characters and give it a name, call that the Gelfand Spectrum of unital C-star algebra. But the question is, what topology should I put on the Gelfand spectrum? And there is a very natural topology to put from our knowledge of functional analysis. Of course, what we want to put as a topology is a weak star topology. After all, we saw that characters are element of the dual of A. They are continuous linear functionals, and they actually have norm 1. So not only are they in the dual of A, they're in fact in the closed unit ball of the dual of A, which, of course, we know by the Banach-Eilhoglu theorem is a weak star compact set. So is a Gelfand spectrum also a nice compact space for the weak star topology? And the answer is yes, it is. So here I remind you briefly of what a net of characters converging in the weak star topology to something means, and it simply is convergence pointwise. So suppose that we have omega j, a net of characters, and it converge in the weak star topology to some omega that at the moment I don't know is in the spectrum. I do know it's a continuous linear functional, but then if you plug the unit of your C-star algebra in this limit right here for your choice of a little a, then you see that since omega j at the unit is always 1, then the weak star limit of characters at the unit of the C-star algebra must take the value 1 as well. So certainly already omega is not trivial, it's not 0. And second of all, we have to check that it's an algebra morphism, but that's fairly easy as well, because if you take a and b in your C-star algebra, then omega j of ab is omega j of a times omega j of b for any j in your index set j here. So as multiplication is continuous, we get that the limit of the product is the product of the limit, and from there we conclude easily that omega is also an algebra morphism. So it's a non-zero algebra morphism, and therefore it is a character. So that proves that the Gelfand spectrum is closed in the weak star topology, but it is a weak star closed set inside a weak star compact set, namely the closed unit ball of the dual of A of the C-star algebra, and therefore it itself is weak star compact. So, long story short, there is a natural object coming out of the characters called the Gelfand spectrum, which is a set of all the characters endowed with a weak star topology, and which immediately becomes a compact space. And since the weak star topology is Hausdorff, it in fact immediately becomes a compact Hausdorff space. Now, so far so good. I haven't actually had to use any sort of Abelian property, so all my definition here involve unital C-star algebras with no specific expectation that the multiplication is commutative. But at this point, we should ask a question, and it is, are there actually characters of an arbitrary unital C-star algebra? Or is the Gelfand spectrum possibly empty? And the answer is, as a little exercise you can check, that indeed the Gelfand spectrum can very much be empty on a unital C-star algebra. And an example would be, for instance, the C-star algebra of 2x2 matrices. We are now going to turn to the case where we work with not only unital C-star algebra, but unital Abelian C-star algebras. And in that case, the work we are now going to do is going to prove that, in fact, there are many such characters. So, if I have a unital Abelian C-star algebra, I'm actually going to construct a star isomorphism from that unital Abelian C-star algebra to the C-star algebra of continuous function on the spectrum. And that star isomorphism is called the Gelfand transform. It's defined like this. If you take an element A in your unital Abelian C-star algebra, then you define A hat, or the Gelfand transform of A, as a map over the spectrum of A, that to any character phi in the spectrum of A maps the value phi of A. Okay? Phi is a linear functional, among other things, from A to the complex number. So here we have indeed a function that to any character gives me a number. Now, the statement of the definition here claims that actually the Gelfand transform of an element of the C-star algebra is an element of the continuous function on the spectrum, not just a function, but a continuous one. And we can check that it's actually straightforward, and it is because we chose the weak star topology as our topology on the spectrum. This was a very smart move. You see, if you pick an arbitrary converging net in your spectrum, let's call it omega j here, and you look at, and the limit is called omega, and you take an arbitrary element x in your C-star algebra, then if you compute the Gelfand transform of that element at omega j, by definition is just a symbolic manipulation. This is just equal to the character omega j evaluated at x, and what weak star convergence tells us is that that converges to omega x. It is, after all, pointwise convergent, but omega x again is the Gelfand transform of x evaluated at x. So Gelfand transform of an element of the C-star algebra is an element of the continuous function on the Gelfand spectrum. So, well, this is interesting because we have a map between those two objects, both, the domain, which is a unital Abelian C-star algebra, and the codomain is another Abelian unital C-star algebra, but the codomain is explicit. It's continuous function on a space. And so we'd like to know, well, what sort of map have we defined? It's clearly linear. Okay, that's step one. We'll get over that again, but it should be clear it's linear. Is it more? Is it a morphism, a star morphism, a star isomorphism? Let's study that. So, to kind of, fix everything in a concrete setup, I'd like to see what happens in the example that I mentioned at the introduction, that is the special C-star algebra of continuous function on a compact Hausdorff space. Alright, so what are the characters of that? Well, the characters that we already discussed. We saw that they are essentially the points, or more precisely, they are the evaluation maps at the points, called delta x, for x a point in my space here. So the Gelfand spectrum is a collection of all of those evaluation maps, or if you prefer, integrals against Dirac measures. And it's endowed with a weak star topology, so it's an interesting exercise to check that the canonical bijection, which to a point in the space associates Dirac measure or evaluation map, is now an homeomorphism. So what is a Gelfand transform of an element? Well, it takes a point in the spectrum, so a delta at some x, where x is a point of my space, and we've seen that there's a bijection, so I know there's a unique x here, so I can simply calculate f of x as the value that the Gelfand transform of f assumes at the map delta sub x for any point x in your space. And typically we actually identify the Gelfand spectrum of C of x simply with x, and if we do that, then the Gelfand transform simply is the identity. So now I want to continue my study of the Gelfand transform, and in fact I want to prove again that it is actually a star isomorphism, and to do so I'm going to start with a really interesting observation that's actually valid for any unital Abelian Banach algebra. We're not going to use a star structure in this proof, but I will state it within the context of this lecture as if A is a unital Abelian C-star algebra, and if you pick an element x in your C-star algebra A, then the spectrum of x as an element of this C-star algebra is actually equal to the spectrum of its Gelfand transform. Now note that the Gelfand transform of an element is a function, c-valued function on the spectrum, so its spectrum is actually its range. So this is actually a very interesting theorem, and let's have a look at its proof. The first thing I'm going to do here is I'm going to prove informally that the Gelfand transform preserves invertibility. So what I mean is the following. First, let's pick x, an element of your C-star algebra that is invertible. If you take a character of the C-star algebra and you apply it to x, we get a non-zero number. We have many ways we can see that. We've seen the proof of that in previous slides. The fancy but overkill way is to note that the omega applied at x is an element of the spectrum of x, and x is invertible, so 0 is not in there. But since this is true for every character, that is for every point in my space, I have that the Gelfand transform of x, when evaluated at every character, is never 0. That exactly tells me that x, the Gelfand transform of x is invertible indeed. Now, let's do the converse. That is, let's say that we have an element of our C-star algebra, again, call it x, but it is not invertible. And I want to show that the Gelfand transform of that x is also not invertible. So how am I going to do that? This is actually the important part of the proof. So what I'm going to do is I'm going to take the principal ideal generated by x. And because here I'm living in a nice Abelian C-star algebra, I know exactly what the ideal looks like. It looks like the set of products of the form x times a, where a ranges over your C-star algebra. And I claim that this ideal is either proper or equal to the singleton 0. So in other words, in less fancy terms, the unit does not belong to this ideal. Why? Because if the unit belongs to this ideal, then there is an a in your C-star algebra that x times a equals the unit. But then, because the algebra is Abelian, a times x is also equal to the unit, and we conclude from that our x would be invertible, which contradicts our assumption. Now, an ideal that's not containing the unit must actually be contained in a maximal ideal of my C-star algebra, and this is a Zorn-Naimark argument, and again, owing to the general theory of Abelian unital Banach algebras, this maximal ideal is itself proper, so this is interesting because it means that the quotient of your C-star algebra by this proper ideal, well, it's simple, and it's not trivial, and it's Abelian. It's Abelian because, well, the algebra is Abelian. It's simple because if I had an ideal in it that's a proper ideal in that quotient, then you can pull it back through the canonical surjection to an ideal in the C-star algebra that would strictly contain the maximal ideal m here, not denoted m here, that we chose. That would be a contradiction. And it's interesting because it's a non-trivial object. In fact, it's a unital algebra because the unit is not in your maximal ideal. Therefore, it has a non-trivial class in the quotient. That's of course the class of which is of course the unit for the quotient. What is that? But the Banach-Mazur theorem that's isomorphic to the complex numbers. So, alright, that means that you have a map, which is an isomorphism of algebras, that goes from the quotient of your algebra by this maximal ideal of our choice onto the complex numbers. And then you have the canonical surjection from the algebra to that quotient. Composing them together, I get an algebra morphism from the algebra, C star algebra A, to the complex numbers. And as I discussed, it's unital. It maps the unit to unit. In particular, it's not zero. And therefore, it's a character. Okay. Nothing here involves a star operation. And therefore, I can also rewrite my maximal ideal here that I chose as a kernel of that character. So why is it relevant? Well, because we need to go back to what little x is about. You see, this maximal ideal we chose contain the principal ideal generated by x, and in fact, in particular, it contains x. So x is in the kernel of that character I just constructed, and therefore the Gelfand transform of x at this character, seen as a point in the Gelfand spectrum, is 0. Alright, so with much effort, we've shown that if you have a non-invertible element x in your sister algebra, its Gelfand transform must vanish at some point in the Gelfand spectrum. Interestingly, at this point in the proof, we have shown in particular that in general, Abelian sister algebras with a unit have a lot of characters. So this is where the Abelian property is used, since we know that there are non-Abelian sister algebras with no character, and it's used many times. It's used in the description of the ideal for x. It's also used in the application of the Banach-Mazur theorem. Now, Banach-Mazur theorem does not require the quotient to be Abelian. Okay, it says that if you have a division ring that's a Banach algebra, then it must be the complex number. However, what happens here is that to know that every non-zero element of that quotient is invertible, I'm using the fact that I have a simple Abelian algebra, and that automatically means that if you take an element of that quotient, if you generate an ideal from it, if that element wasn't 0, then your ideal has to be everything, and therefore, in particular, since we have a unital quotient, the unit is in this ideal, and again, thanks to the Abelian property, it tells us that the element must be invertible. So this is the crux of the proof. After that, it's fairly easy. We've proven that the Gelfand transform of an element x of your sister algebra is invertible if and only if x is invertible. So putting as a negation of this is that the Gelfand transform of an element is not invertible if and only if that element is not invertible. And therefore, if you take any scalar t, then x minus t as an element of your sister algebra is not invertible if and only if its Gelfand transform is not invertible. But its Gelfand transform can be easily seen to be the Gelfand transform of the element minus t. So in other words, now you see the relationship between the two spectrums. They must be indeed equal as announced. This is a very nice theorem among many consequences, since in any Banach algebra with a unit, every element has non-empty spectrum. You see that for unital Abelian sister algebra, this result certainly emphasizes that there are many a priori characters, enough that we can recover the spectrum of any element using the characters of the algebra. And as I explained, that really does hinges on commutativity here. Alright, so we are now in position to prove our main theorem, the Gelfand-Naimark Theorem. What it says is, essentially, the Gelfand transform is a star isomorphism. It's a very deep result. Let's prove it before we discuss it a bit further. So, what do I need to prove? Well, I need to prove a lot of things. I need to prove the Gelfand transform is an algebra morphism, so it has to be linear, it has to be multiplicative, I would like it to be unital, I'd like it to be injective, and onto. The first step is let's prove it's linear. So if you take any two x and y in your sister algebra and some scalar t, then if you calculate the Gelfand transform of tx plus y applied to some character omega, it's simply omega of tx plus y. But omega is linear, so you apply this and you observe that you indeed get that the Gelfand transform of tx plus y equals to t times the Gelfand transform of x plus the Gelfand transform of y. So here we use the linearity of omega. Next, I'm going to use the fact that characters are also multiplicative. So it's important because this is a property that makes things different between Abelian and non-Abelian world. There are lots of continuous linear functional of mass 1, of norm 1, for instance, by the Gelfand-Naimark theorem. What is restrictive here and what makes characters sometimes not even exist in non-commutative system algebras is that we require this multiplicative property. So what role does it play? Why do we need to impose this hard condition? Well, here it comes. If x and y are two elements of your system algebra and you evaluate the Gelfand transform of their product at some character omega, then it's omega of x times y, but because omega is multiplicative, that is indeed omega of x times omega of y, which is the Gelfand transform of x at omega times the Gelfand transform of y at omega. The unit of the system algebra is mapped to the unit of the codomain of the Gelfand transform. That's immediately clear because we've seen that every character is at 1 at the unit takes the value 1. So before I look at the relation between the adjoint operation and the Gelfand transform, I'm going to list one more property that, like the one I've proven so far, if you pay attention, does not actually depend on the C-star structure. It just depends on working in a unital Abelian Banach algebra, and that is that the range of the Gelfand transform must be dense, which is quite interesting. And the way it works is I'm going to use the Weierstrass theorem. So if I take any two characters of my C-star algebra, omega and psi, and they're not the same characters, well, then that means that they're different at some point in your C-star algebra. They're functions on the same space and so on. The reason why they're different is because there's at least one point where they don't take the same value. Call that point x. So it tells you that the Gelfand transform of x at omega is not equal to the Gelfand transform of x at psi. Range of the Gelfand transform separates the point of the spectrum. It also contains the constant function equals to 1. So by the Weierstrass theorem, automatically we get that indeed the range of the Gelfand transform is dense in the continuous function on the Gelfand spectrum of your system algebra. Alright, so now let's look a little bit at the star structure as well, the adjoint. So we worked quite hard to prove that every character is actually a star morphism. This is where it comes into play. If you pick an element x in your system algebra and you want to evaluate the Gelfand transform of the adjoint of x at some character omega, by definition this is omega of the adjoint of x, and that we proved is a conjugate of omega of x. In other words, the conjugate of the Gelfand transform of x at omega. And so again, if you forget the middle equalities here and look just at the ends, you see we've seen that the Gelfand transform is a star morphism. And it's unital, so it's a unital star morphism. So that's interesting. At this point, we know things about the Gelfand transform now. We know that it has norm 1, it's continuous, and it has norm 1. But we're going to improve even more. And this is where my result about spectra being preserved by the Gelfand transform comes into play. In order to conclude, normally I need to prove that my Gelfand spectrum is at once injective and surjective, right? I mean, we need both, so that we have a star isomorphism. But it turns out that I'm going to get both in one argument because, well, we have a hint. We learned that star isomorphisms of unital system algebras are always isometries. So it stands to reason that maybe I should just try to prove that my Gelfand transform is an isometry because it's going to be at the end if I'm right. And the interesting part of that is that if it's an isometry, then of course it's injective. But also, because it's an isometry, it will map the complete space that is my Abelian system algebra here to something complete inside the space of continuous function on the spectrum. Okay? But if the range is complete, it's closed. And since we already know it's dense, it will be everything. So it actually boils down to showing that the Gelfand transform is an isometry. And why would it be an isometry? Well, as I say, I know that the Gelfand transform preserves spectra, which in general does not give me enough information for an arbitrary Abelian Banach algebra, but in this case, it gives me a lot of information because I work in a C-star algebra, and there are those very important elements called the self-adjoint elements. What's important about them is that their spectral radius equals their norm. So let A be a self-adjoint element in your C-star algebra. since the spectrum of A equals the spectrum of its Gelfand transform, we can conclude that the norm of A, which is the spectral radius of A, is equal to the spectral radius of its Gelfand transform. But then we have two ways to conclude. Well, you can either conclude that the Gelfand transform of a self-adjoint element is actually self-adjoint owing to the star morphism property of the Gelfand transform, and therefore again its spectral radius is equal to its norm, and by transitivity we get the announced identity that the Gelfand transform is an isometry on the self-adjoint element. Or you could bypass this and simply note that the spectral radius of a function is by definition its norm. It's simply literally the definition of the norm that tells you that. But in any case, we've seen that because the spectrum of an element and the spectrum of its Gelfand transform are identical, for self-adjoint element in particular, we can conclude that the norm of a self-adjoint element equals the norm of its Gelfand transform. And then you use the C-star identity to conclude the Gelfand transform is an isometry. So we use the fact also that the Gelfand transform is a star morphism. So the idea is you pick an arbitrary element A in your C-star algebra. Alright, so we know that the square of the norm of A is equal to the norm of A star A. But then A star A is self-adjoint, so that's equal to the norm of the Gelfand transform of A star A. And then since the Gelfand transform is a unital star morphism, that's indeed equal to the norm of the adjoint of the Gelfand transform of A times the Gelfand transform of A, which is, because we have a codomain here that's a C-star algebra, equal to the square of the norm of the Gelfand transform of A. So in other words, for any element A of your C-star algebra, you prove that the square of the norm of A equals the square of the norm of its Gelfand transform. And from there, we deduce immediately the Gelfand transform is an isometry. So to put all that together, we have a unital star morphism, which is also an isometry from a complete space to some space and has a dense range. Putting all that together, you get that we have indeed proven the Gelfand transform is a star isomorphism. This is a very beautiful, very deep result. So let's not stop here. Let's start discussing what happens to star morphisms between Abelian unital C-star algebras. I mean, we have a characterization of spaces. Can we express somehow star morphism in terms of maps between their Gelfand spectra? And the answer is yes, and it's not even that hard to do anymore. So let A and B be two unital Abelian C-star algebras. If pi from A to B is a unital star morphism, then there exists a unique continuous function, which I'm going to call pi hat, or the Gelfand transform of pi, from the spectrum of B to the spectrum of A, such that we have this relation. For any element A in your C-star algebra in the domain, then the Gelfand transform of pi of A equals to the Gelfand transform of A composed with this pi hat. So to prove this, we're just going to use our knowledge of, the Gelfand-Naimark theorem. I take a character in the spectrum of B, and I want to associate to this character a character of A through a map that I'm going to call pi hat, so that I have the relation stated in the theorem. So how am I going to do that? It's actually quite easy. If omega is in the spectrum of B, I define a point in the spectrum of A that is a character of A simply by setting pi hat of omega to be omega composed with pi. Both pi and omega are unital star morphisms, so their composition is a unital star morphism from A to the complex numbers in this case, and therefore it is a character of A. And, well, we have a map already, pi hat. We just want to check it's continuous, and that really again follows from the definition of the weak star topology. So if you take a net omega j of characters in the spectrum of B that converges for the weak star topology to a character omega, and if you take an element D in your C-star algebra A, and you calculate what is pi hat of omega j applied to D. Remember, pi hat of omega j is an element of the spectrum of A, so it's a function on A, can apply to an element. But then you unwind all this definition, and you end up with this is calculating omega j at pi of D, and all of that converges by the definition of weak star topology to omega of pi of D, which is indeed pi hat of omega at D. So you see pi hat, it is a continuous map. And that's it. That's our proof. So let's turn to the uniqueness property of our pi hat. So we constructed for a fixed a unital star morphism pi, a pi hat map, continuous map from the spectrum of B to the spectrum of A with the desired property, but maybe there is another continuous map from the spectrum of B to the spectrum of A with the same desired property. Let's see that, in fact, such a map would have to be pi hat. There's no choice. So assume they're different, which, since they're function on the spectrum of B, means there is a character of B on which they take a different value. But the Gelfand transform applied to the C-algebra A separates the point. In other words, we actually know that the Gelfand transform applied to the C-algebra A is the entirety of the continuous function on the spectrum of A. So given that, it separates points, so there must be some element in the range of the Gelfand transform. In other words, there must be the Gelfand transform of some element of your C-algebra that takes two different values at pi hat of omega and rho of omega. Okay? And this is absurd. Why? Well, because what is the Gelfand transform of A applied to rho of omega? Well, you look at the definition. That should be the Gelfand transform of pi of A, evaluated at omega. But so should be the Gelfand transform of A applied to pi hat of omega. That, again, by our property, should be the Gelfand transform of pi of A applied to omega. That's the definition. And since it's the same pi on both ends, it's the same value. So we have a contradiction, and rho must indeed be the Gelfand transform of pi. So with this uniqueness, we can have a really cool conclusion. If you have three unital abelian C-star algebras, A, B, and D, and you have a unital star morphism from A to B, let's call that pi, and another unital star morphism, let's call that rho, from B to D, then you can calculate the Gelfand transform of rho composed with pi, which is, by the way, a unital star morphism from A to D. And it equals to, in fact, the Gelfand transform of pi composed with the Gelfand transform of rho. The proof simply consists in checking that this Gelfand transform of pi composed with the Gelfand transform of rho satisfies the desired equality stated in my theorem, because by uniqueness then we will conclude the stated identity. That's just a simple quick calculation. Okay? So if you have two compact Hausdorff spaces x and y, and a function f from x to y that's continuous, then I can make a star morphism from C of y to C of x. And the way it works is you take a function in C of y and you compose it with that f, and it gives you a function in C of x. And that's a star morphism, and you could calculate its Gelfand transform, and again with the identification of the space x with the Gelfand spectrum of C of x and the space y with the Gelfand spectrum of C of y that we discussed before, then suddenly, again, the Gelfand transform of this star morphism we build is simply the original function f. So you start from f, a function between spaces, you get a star morphism from the C-star algebras of these spaces, but with the order flipped, the domain and codomain switched, and then you can Gelfand transform that morphism to get back the function you started with. Alright, well, to summarize everything we've done in this lecture, here is a theorem that I think is very exciting and really not only deep and interesting, but beautiful and inspiring, certainly in the sense that a lot of mathematics came out of this observation. The category of compact Hausdorff spaces with continuous maps for morphisms is dual to the category of Abelian unital C-star algebras with unital star morphisms via the following contravariant functors. So to a unital C-star algebra that's Abelian, you associate its Gelfand spectrum, which gives you a compact Hausdorff space, and to any unital star morphism, we associate the continuous function that's the Gelfand transform of that unital star morphism. And on the other side of things, to any compact Hausdorff space, we associate the Abelian unital C-star algebra of complex valued continuous function on that space. And to any continuous function, you associate the associated unital star morphism by composition. And you can check that these two functors that are described by these two bullet points are in fact dual to each other. So what it means very informally, and I'll let you work that out, is that if you apply a functor and then apply the next, you get from, it becomes an endofunctor of whatever category you started from. And this endofunctor is not the identity per se, but through a set of natural transformations, it's equivalent to the identity endofunctor. And this works either way. Philosophically, what it means is that everything you can say on the topology of a compact Hausdorff space, you can rephrase it in a theorem about unital Abelian C-star algebra. It's the same theorem, but you can rephrase it in purely C-star algebraic terms. Okay. So now, of course, we would like to know what happens if we drop the adjective Abelian, and also what happens if we drop the adjective unital. We will start by dropping the Abelian condition and study what is called the Gelfand-Naimark Theorem in the next lecture.